Hi, my name is Aditya Vadapalli, and in this talk, I'm going to talk about our paper, You May Also Like Privacy, which is a private recommendation system, and this is joint work with Fatine and my PhD advisor, Ryan Henry. So let's begin. We'll begin with the usual Netflix example, and here we have our friend Bob, who logs into Netflix and watches the movie Invictus. The next day, he watches the movie Shawshank Redemption. And by this time, Netflix has learned a few things about Bob and recommends the movie Bucket List to him, hoping that he would enjoy movies that feature Morgan Freeman. Indeed, Bob enjoys this as well. And now, now the Netflix algorithm has learned a few more things about Bob, and now recommends the movie 12 Angry Men. Now hoping that he likes movies in the drama genre, and once again, Netflix is correct. And in this process, Bob really gets to watch a lot of movies of his choice without him having to search through the various Netflix movies. And this whole process of data collection and thus getting personalized recommendations for him works very well for him. However, things are not all honky dory, and this entire process of data collection has had a lot of negative effects, as it has been well studied. For instance, that it leads to algorithmic discrimination, erosion of democracy, identity theft, and whatnot. So, in many ways, this entire thing is a bit of a double-edged sword. For instance, while it gives us personalization with data-driven creation, useful recommendations, and also and other advantages like fraud detection, it comes with these negative effects of things like chilling effects, algorithmic discrimination, and identity theft. So the question that we ask in this paper is it possible to build a media delivery system that gives personalized recommendations while hiding the consumption history? At the outset, this seems like a rather unlikely thing to happen. However, let's have a look at this more carefully. And first, let's answer the question about hiding the consumption history. The simplest way to hide consumption history is as follows: is basically to ask the database for certain record, and then download the entire database and then look at the record of your choice. While this works, it's completely impractical because, for instance, if one wants to watch one particular movie in Netflix, it would be completely infeasible to download the entire catalog to watch one movie. Private information retrieval has been well studied in the literature and has been used for hiding consumption history. And a very informal definition of PIR is that the users want to download something from the database without the servers knowing what they downloaded. First, let's have a look at the non-private information retrieval method in the slightly odd manner, where there's a database D and the user would like to download the lth record of the database. And what they do is that they send a standard basis vector at L, that is a vector which is zero everywhere except at the lth location where it is one. And the servers return back the dot product of the standard basis vector at L with the database, and indeed the user gets the lth record of the database. However, this is not private because it leaks the index L. So one of the many ways to make it private is to have n replicas of D with n servers, and the user, rather than sending one standard basis vector, sends the secret shares of the standard basis vector to these n servers, and the servers return back the dot product of the secret shares with the database, and the user can reconstruct these dot products to get the lth record of the database. While this works properly, while this is correct and it is private unless all the n servers collude, the problem, of course, is that these vectors are really large and they are as large as the size of the database, as the height of the database. So this is where distributed point functions come into picture. These were introduced by Gilboa and Desai in 2014, improved upon by Boyle, Gilboa, and Desai in 15 and 16. So first let's look at the definition of point functions. So point functions are these special functions over a certain domain, which evaluate to zero at every point in the domain, except at one special location, which we call as a target location, where they evaluate to a special value, which we call the target value. And DPFs are a succinct way to share these point functions. The tuple Ly describes the point function, where L again is the special point and Y is that special value. Now, let's talk about DPFs. And there are two main algorithms associated with DPFs. And bear in mind that here we are talking exclusively about 2 DPFs. That is uh, that is where we are interested in sharing the point function among two servers. The first algorithm associated with DPFs is the generator algorithm, which the client runs, and the generator takes in as parameter a security parameter lambda and the description of the point function L and Y. And it returns back two DPF keys. The client sends these DPF keys to P0 and P1, who run the second algorithm associated with DPFs known as the evaluation algorithm. The evaluation algorithm takes in as input the DPF key and some index from the domain of the point function. These outputs of the eval function look completely random to P0 and P1, but they have some special properties. These outputs XOR to 0 at every location in the domain except at the target location where they XOR to the target value y. Um, there's also a function called eval full associated with DPFs, which essentially evaluates the DPF over the entire domain. So essentially, eval full of DPF is a vector comprising of the evals of DPF over the entire domain of the point function. Naturally, eval full of DPF0 and eval full of DPF1 are the secret shares of the standard basis vector at L scaled by Y. Now let's talk about the construction of DPFs, and this construction is due to Boyle, Gilboa, and Desai from their 2016 CCS paper. There are two main ingredients that are there for the construction of DPFs. One is the length doubling PRG, which is used to construct these binary trees like this. So P0 and P1 get some random seeds, and they use a length doubling PRG to construct a binary tree such that the number of leaves is equal to the size of the domain. Their goal eventually is to have the leaves of the binary tree correspond to the outputs of the eval function. For instance, if they want to find if they want to evaluate at index say 5, the fifth leaf should essentially give the output of the eval function at the index 5. Now, naturally, what they would want is that the leaves of the two trees should be identical at every location except at the target location, where and at the target location the leaves should XOR to the target value. Of course, just using this length doubling PRG would lead to completely random trees and not what we're looking for. Therefore, there's a second ingredient associated, that is the correction words, which turn these random which turn these random values into equal values. And what essentially happens is that all the leaves except the target leaf are made equal to each other for both the trees, and the target leaves remain random. This is almost complete, except the fact that what we want in the target location is the target value, not some random value. And even that can be corrected pretty easily just by having another correction word known as the final correction word, which basically turns this random value into the correct target value. Now, with the help of DPFs, one can construct various PIR protocols, and one such PIR protocol is the Hafiz-Henry PIR protocol that appeared in PETS 2019. This PIR protocol is extremely fast and it can enable private streaming videos. Now with this, we solve the first part of our problem, that is hiding the consumption history, but the second part still remains, that is to provide personalized recommendations. The way we do that is by doing secure multi-party computation over these DPF-based PIR queries. The system we built is called Persona because it is built on top of PIR, and it has the following key features. Suppose a user I has queried for an item J, Persona would be completely oblivious to J. However, Persona would know I, the user who's authenticated. That is, we essentially hide what the user queried for, but not the user themselves. Now next talk about the collaborative filtering algorithm, the underlying algorithm that is used to provide recommendations. It is based on gradient descent, and there are two matrices, known as U and V, called the user and item profiles. At each iteration, the user and item profiles are updated in the following manner. If a user I has queried for item J, one takes the dot product of the ith user profile with the jth item profile and multiplies with the corresponding user or item profile and adds them to the user or item profiles. Once this is done, the user and item profiles have to be normalized. So let's look at the setting. Persona system requires at least 4 servers for multi-party computation, and more than 4 servers would make the PIR efficient. Now, these servers hold the shares of the user and item profile. Here, V0 and V1 are the shares of the item profiles, and U0 and U1 are the shares of the user profiles. The user sends these Hafiz Henry PIR queries, reconstructs the responses to get the movie of their choice. Once that is done, the persona servers engage themselves in an MPC protocol to provide the recommendations. Now let's look at each of the steps of the collaborative filtering algorithm. The first step is to update the user profiles. And now it is done by this following equation. Now let's have a look at UI. UI is easy to compute because I is known, because persona doesn't hide the user. Now computing Vj is not that trivial because P0 and P1 have the shares of the item profile matrix, and they need to compute the shares of the jth item profile. So this is the problem essentially, that they would like to compute the shares of Vj. For this purpose, we built an MPC gadget called DPF-based multiplexer, the details of which are there in the paper. So the DPF-based multiplexer gives us the shares of Vj. Now, once we have the shares of Vj, the jth item profile, we already have the shares of the ith user profile. One can compute the dot product using standard MPC protocols like the Duatala protocol, which is a variant of the Beaver triple multiplication. And once that is complete, multiplication with Vj is again using standard MPC, and the user profiles can be updated. The next step is to update the item profiles, which is more complicated than updating the updating the user profiles. Once again, computing this particular value, that is Vj plus Ui multiplied by this entire dot product, is not very difficult, and that requires just the standard MPC protocols. And now suppose that P0 and P1 hold shares of Z, which is essentially this particular whole value. They want to add Z to the jth item profile. Now this seems almost like PIR write, except that there is a key difference. Unlike in PIR write, the user cannot create DPFs whose target value is Z, because Z is computed is computed while the collaborative filtering algorithm is taking place. In other words, the gadget that we call to do the gadget that we use to do the item profile updation is called demux, and the demux and the DPF based demux and PIR write, the key difference is that the input wire is not fixed. So the way we solve this problem is as follows. Now recall what was the main problem in the main problem was that there was no way for the user to construct DPFs that would have the target value as Z. So now let's recall the construction of DPFs. There was this notion of final correction word which turned the random value at the target location into the desired value, the target value. So what the user does is that it withholds the final correction word and sends this defoliated DPFs, that is DPFs with a random value at the target location. Now these DPFs might seem useless at the outset. However, what the user also does is that it sends the shares of T2 plus T2 tilde, where T2 and T2 tilde are the random values at the target location. Let's call the shares of T2 and T2 tilde as CW0 and CW1 respectively. So now P0 holds Z0 and CW0, and P1 holds Z1 and CW1. Z0 and Z1 are shares of Z, the value with which they want to update the item profiles. Now they exchange Z0 plus CW0 and Z1 plus CW1 and get CW prime, which is Z plus T2 tilde, which they can use as a final correction word to get the desired DPF. Now with this, they can update the item profiles. Now once that is complete, the next step is to do the normalization. Now that the normalization problem is as follows. P0 and P1 hold x0 and x1 vectors such that they add up to x, and their goal is to compute x over the square root of the dot product. Computing the dot product is not difficult, and once the inverse square root is computed, normalizing is just one multiplication. So the problem is about computing the inverse square root. So the way we do it is, rather than computing the inverse square root, we compute the linear approximation of the inverse square root. So what we have essentially is a table like this, where we have ranges of x and the corresponding slope and intercept, which would make a good linear approximation. For example, from this table, if x lied between say x3 and x4, m4x plus b4 would be a good linear approximation of 1 over square root x. Now, of course, the main problem is to compute is to get the correct shares of the slope and intercept. Now, it almost seems like a PIR problem, except for the fact that constructing the PIR queries is not trivial because rather than having x, the parties only have shares of x. So let's have a look at the problem again. P0 and P1 hold shares of xi, and the main idea is to somehow compute the main idea is to somehow compute the PIR queries for xi. However, the main roadblock, as we said earlier, was that none of the parties know xi. So we have a key observation though. The observation is as follows. Suppose P0 and P1 held shares of a standard basis vector at some completely random value. And then suppose the random value was 5 in this example. And then they cyclically shifted by right these shares of the standard basis vector at that random value, 5 in this case, by xi minus 5, that would give them the shares of the standard basis vector at xi. Now, using this key observation and P2, we construct we construct the protocol to do to compute the inverse square root. P2 generates the DPF at some random value alpha 0 plus alpha 1 and sends the DPF keys along with alpha 0 and alpha 1 to P0 and P1 respectively, who hold x0 and x1. P0 and P1 then do an eval full on DPF0 and DPF1 to get the shares of the standard basis vector at alpha, which is alpha 0 plus alpha 1. Next, they exchange x0 minus alpha 0 and x1 minus alpha 1 to get xi minus alpha, and then cyclically shift the outputs of the eval function to get the correct PIR queries. And with that, they can get the correct slope and intercept, and then compute the inverse square root, with which they can compute the normalization. So persona can be summarized as follows. We use two DPFs to do PIR, then use distributed multiplexer and demultiplexer to update the user and item profiles. That is, we do collaborative filtering on these PIR queries, and then use a fast PIR-based normalization to complete the algorithm. So we implemented persona and ran it on Amazon EC2. The servers were placed in geographically distant locations to mimic the real-world latency, and our results were quite outstanding. Netflix, for instance, has 2 to the 14 titles across all catalogs, with around 110 million subscribers worldwide. Our training is not sensitive to the number of users, and if Persona can actually train around 2 to the 15 queries on 2 to the 49 items in a minute, which means that with a very modest charge, Netflix can actually pay for around a 40-node persona and train on 100% of the Netflix data. One can find other evaluations of persona, for instance, the way persona scales with number of items, the way it scales with number of queries, and the way it scales with the dimensions of the user and item profiles in our paper. We also find that persona is way faster than for instance, other methods that have been used to implement these private recommendation systems. For instance, one of the methods is to use garbled circuits, and Persona is almost 5 times faster than that. Yeah, and with that, I conclude the talk, and I'm happy to answer any questions.